Welcome to the Art of Electronics video lecture series. This is our very first video, and we're starting with the basics: voltage, current, and resistance. Here are the subtopics we'll cover today. Watch till the end of this lesson and you will have a solid understanding of all the basic concepts of electronics. This is the first step toward becoming the Picasso of electronics. First, we should know what learning electronics means. The art of electronics starts with understanding the atom. Everything around us is made of atoms. Imagine an atom as a tiny solar system, with a nucleus at the center and electrons orbiting around it. The nucleus is packed with protons. These tiny particles are the building blocks of everything, from your hair to the stars in the sky. Now picture this. If we bring an electron and a proton closer together, they attract each other like magnets. But what happens if we have two protons or two electrons? They repel each other, almost like trying to push the same poles of two magnets together. Why does this happen? Early scientists had a brilliant idea to explain this. They proposed that these tiny particles carry two types of charges that behave oppositely. They noticed that opposite charges attract each other, while like charges repel. This simple model answered many questions about the behavior of charged particles. Naming these charges could have been a complex task, but our early scientists took the easy road. Instead of inventing new names, they simply called them positive and negative charges. And just like that, they laid the groundwork for understanding the electrical forces that power our world. And that's how electrons came to be known as having a negative charge, while protons got labeled with a positive charge. This is a piece of metal, and it consists of trillions of tiny atoms. As I mentioned earlier, these atoms contain electrons. These electrons can actually be separated from their atoms and set into motion. In electronics, we use various techniques to control this movement and accomplish amazing things. So learning electronics is all about mastering the art of controlling electrons and harnessing their power to create incredible devices and systems. It's like having the keys to unlock limitless possibilities. Now let's move on to conductors and insulators. Not every material allows electrons to move through them. The materials that do allow electrons to flow freely are called conductors, like metals. These are the superhighways for electron traffic. Materials that do not allow electrons to flow are called insulators. They block the path of electrons like a roadblock. Silver is considered the most conductive metal at room temperature. However, we usually use copper wires in circuits because it's cheaper and still has excellent conductivity. Materials such as rubber and glass are insulators. They don't allow electrons to flow freely, which makes them perfect for protecting us from unwanted electrical currents. Not all conductors treat the moving electrons the same. The degree to which a material conducts electrons is known as its electrical conductance. The opposite of conductance is resistance. Resistance measures how much a material resists the movement of electrons through it. As I mentioned earlier, electrons repel each other. They really don't like being crowded together. Imagine we have two areas: Area A, which is packed with electrons, and Area B, which has only a few electrons. The electrons in Area A are very unhappy because they're crammed into a small space, creating a lot of electron pressure. In contrast, the electrons in Area B are less unhappy because they have more room and don't feel that same pressure. Now, if we connect these two areas with a conductor, the electrons will move from Area A, where they are crowded and uncomfortable, to Area B, where there's more space. This movement happens because of the electron pressure difference. It's a fundamental concept in understanding how electricity flows. Now, this is really amazing. We know how to move electrons from one place to another. All we need to do is create an electron pressure difference and connect those areas with a conductor. Look at these two areas with different electron pressures connected by a conductor. The electrons move from high pressure to low pressure. In physics, this electron pressure difference is known as voltage. Voltage measures the tendency of electrons to move from one place to another. It's like the push that gets the electrons flowing, making it a crucial concept in the world of electronics. By understanding and controlling voltage, we can direct the flow of electrons to power everything from tiny gadgets to massive machines. When electrons start moving because of the voltage, we call this movement an electric current. Since electrons are negatively charged, this current is often referred to as a negative current. But we humans don't like negative things. So when there's a negative current flowing in one direction, we call it a positive current flowing in the opposite direction. In fact, almost every time we use the term current, we're actually talking about the direction opposite to the electron flow. It might seem a bit confusing, but that's just how we roll in the world of electronics. This convention helps us keep things simple when designing and discussing circuits. So when you hear current, just remember it's the positive perspective on the flow of those tiny negative electrons. Here we have a battery, which has two sides, positive and negative. The negative side is packed with tightly crammed electrons, creating a lot of electron pressure. On the other hand, the positive side has far fewer electrons, resulting in much less electron pressure. This difference in electron pressure, or potential difference, is what we refer to as the voltage of the battery. Because of this potential difference, the electrons on the negative side are eager to move over to the positive side. It's like a crowd of people trying to move from a packed room to a spacious one. Now let's give those electrons a path using a conductor. When we connect the two sides of the battery, electrons start moving from the negative side to the positive side. This movement of electrons is called a negative current. But remember, since we don't like negative things, we refer to the current as flowing from positive to negative. So while the electrons are actually moving from the negative side to the positive side, we say the conventional current flows from the positive side to the negative side. But there's no point in just letting electrons flow freely. We want to get some work done with their movement. So let's connect a light bulb to our battery. Now we have a complete circuit. The electrons are happy because they can travel to a less pressured area. And we're happy because we get useful work done, like lighting up a bulb. It's a win-win situation. In electronics, what we're actually doing is applying an electron pressure difference and letting electrons move to a low pressure area, making them do some work along the way. Isn't that smart? Now you may wonder, how long does this electron movement last? As electrons leave the negative side, the electron pressure there gradually decreases. Meanwhile, electrons gather on the positive side, increasing the pressure there. Over time, the pressures on both sides equalize, eliminating the pressure difference. When this happens, the voltage drops to zero, and we say the battery is dead. Now let's move on to the current. We define the amount of current by counting how many electrons flow through the conductor per second. If Q coulombs of electrons flow through a conductor in T seconds, the current is calculated as I equals to Q over T. The unit of current is called amperes, or simply amps. 1 ampere equals 1 coulomb moving past a point per second. That means to create a 1 ampere current flow, 6.2 quintillion electrons have to flow through a single point of the conductor every second. It may seem like a huge number of electrons, but at the atomic scale, that's how things are, so don't be surprised. Now, how do we define voltage? As we discussed earlier, we can apply an electron pressure difference and let electrons move to a low pressure area, making them do some work along the way. If the potential difference is large, electrons move strongly from high pressure to low pressure, allowing us to do a lot of work. If the potential difference is small, electrons are less likely to move, so they can only do a small amount of work. Thus, the amount of work that electron movement can produce is a measurement of its potential difference. We define voltage as the amount of work produced by the movement of charge. If the movement of Q coulombs of charge creates W amount of work, we can define the voltage as V equals to W over Q. 1 volt is the potential difference. also known as the electron pressure difference, between 2 points in a circuit when 1 joule of work is done by moving 1 coulomb of charge between those points. Understanding voltage might seem tricky at first, but don't worry, just replay this section a few times and soon it will make perfect sense. Now that we have some knowledge about electronics, let's talk about how we measure voltage and current. How can we measure the voltage across this light bulb and the current going through it? To measure the voltage, we use a voltmeter. To measure the voltage across a component, we connect a voltmeter in parallel with the component, like this. To measure the current through a circuit, we use an ammeter. Connecting an ammeter is a bit trickier than a voltmeter. First, you have to disconnect the circuit path where you want to measure the current. Then connect the ammeter in series and complete the circuit, like this. Let's do an experiment. First, observe the voltage and current in this setup. Here the voltage is 1.5 volts. The voltage of alkaline batteries usually ranges around 1.5 volts. The current seems to be 100 milliamperes, which we can write as 0.1 amperes. Now calculate the ratio between voltage and current. It's 15. Now mark the voltage and current for this setup on the voltage versus current graph. Next, add another battery in series to this setup and repeat the process. Notice that both the voltage and current have increased. Calculate the ratio again. Do you notice it remains the same? Mark these observations on the graph. Add another battery and observe the voltage and current again. Both have increased even further. Calculate the ratio once more, and you'll see it's 15 again. Mark these new observations on the graph. As we continue adding batteries, we will get multiple data points. Let's connect the dots and draw the graph. It's a straight line. This straight line shows the consistent relationship between voltage and current. The ratio between voltage and current for each setup is constant, which means the voltage is proportional to the current. Simply put, the number of electrons moving per second is proportional to the force pushing them to move. Isn't that quite obvious? The gradient of the straight line is constant, representing the ratio between voltage and current. This is a really important relationship. Keep this in mind and I'll explain this further in a few seconds. Now we have two circuits. Both circuits are almost similar. The only difference is the light bulb type. If we repeat the previous experiment, we get results like this. What do you observe from these data? Even though the voltage is the same, the current through light bulb A is less than through light bulb B. This implies that it's harder for electrons to move through light bulb A than B. In other words, light bulb A has more resistance to the current than light bulb B. This concept of electrical resistance is very important in electronics. The electrical resistance of an object measures its opposition to the flow of electric current. It was first introduced by Georg Simon Ohm, who proposed using the ratio between voltage and current to calculate resistance. This electrical resistance represents how much pressure difference or voltage is needed to push a certain amount of electrons through the light bulb. If we need a higher pressure difference, it means the light bulb resists the flow of electrons more. It has high resistance. Conversely, if we need only a little pressure difference, the light bulb has low resistance. We measure this resistance using the unit called ohms. 1 ohm can be defined as the resistance between 2 points in a circuit when 1 volt of voltage is required to flow 1 ampere of current between those 2 points. The definition of resistance gives us the relationship between resistance, voltage, and current. These three quantities are the basic pillars of electrical and electronic engineering. To honor Georg Simon Ohm, we call this relationship Ohm's law. We can express Ohm's law in three forms. Resistance equals voltage divided by current. Current equals voltage divided by resistance. Voltage equals current times resistance. Ohm's law is the most fundamental law of electronics, providing the basis for understanding how electric circuits behave. According to Ohm's law, we can control voltage, current, or resistance by adjusting any two of these variables. Earlier, we talked about batteries. Batteries have designated negative and positive sides. Until the battery is drained, the conventional current flows from the positive side to the negative side. If we neglect the draining of a battery, we can consider the voltage and current to be constant. If we draw the voltage and current of a battery on a graph, it will look like a straight line like this. The problem with the batteries is they have limited capacity. So to run high-power applications, we need some kind of other electricity source. This is where generators come in handy. Generators can produce electricity from motion. Normally, we use a flowing water stream, steam, or a fuel engine to produce the motion, and generators can convert that kinetic energy into electricity. Unlike batteries, which store electrical energy, generators produce electricity whenever needed, so they can be considered a continuous energy source. We will explore the workings of a generator more deeply in our future lessons. According to the laws of electromagnetism, when a current-carrying conductor is placed in a changing magnetic field, a current flow is induced inside the conductor. However, this current changes its direction back and forth, meaning the current alternates its direction. If we draw the voltage and current graph of a generator's output, we will get a graph like this. Let's compare the outputs of a battery and a generator. We can see that the current from the battery flows only in one direction. This is called direct current. In contrast, the current from a generator alternates its direction periodically. This is known as alternating current. These two basic current types, DC and AC, are used in our daily lives. Our homes receive alternating current from the main grid, which powers most of our household electric devices such as lights, heaters, and motors. On the other hand, all of our battery-powered devices use direct current. Now we are going to talk about electrical power. Consider this simple circuit. When we apply a voltage V across the light bulb, a current I starts to flow through it. Let's assume the light bulb does not waste energy and converts all the energy it uses into light. If within the time t, Q amount of charges pass through the circuit and perform W amount of work, we can use the definitions of current and voltage. Current equals to the Q divided by T, and voltage equals the W divided by Q. In physics, we define power as the rate of doing work. Since W amount of work is done on the light bulb during time t, the power consumed by the light bulb is equals to the W divided by T. Now we have three equations, but there are many variables. Let's try to simplify these and develop the relationship among power, voltage, and current using these equations. Let's multiply the equations 1 and 2. We get that the voltage times current is equal to the work divided by time. This is our fourth equation. Pay attention to the equations 3 and 4. Those are equal. So we can say the power consumed by an electrical device is equal to the voltage across it times current through it. This is a crucial relationship in electronics, allowing us to understand and calculate the power requirements and consumption of various devices and circuits. Now, if the resistance of this light bulb is R, using Ohm's law, we can derive two other useful forms of this equation. We measure this power using a unit called watts. If any electrical device consumes 1 joule of electrical energy every second, we say that the device consumes 1 watt of power. All these equations may seem a bit complex at first, but watch carefully and you will understand how these equations are derived. Instead of just memorizing the final equation, try to grasp the logic behind them. This understanding will be a huge advantage in your journey in electronics. By knowing the origin of these relationships, you'll be able to troubleshoot and solve problems more effectively. Let's try to solve a problem. This will give us a better understanding of these concepts. Here we have a resistor with a resistance of 10 ohms connected to a power supply that provides a voltage of 20 volts. Calculate the current flowing through the resistor and determine the power dissipated by the resistor. First, to calculate the current, we can use the Ohm's law. Current equals to the voltage divided by the resistance. The current flowing through the resistor is 2 amperes. Since we now know the voltage, current, and resistance, we can use any form of the power equation to calculate the power. Let's use the voltage and resistance to calculate the power dissipated by the resistor. Thus, the power dissipated by the resistor is indeed 40 watts. Now let's talk about resistors. A resistor is a passive electrical component that creates resistance in the flow of electric current. They can be found in almost all electrical networks and electronic circuits. Imagine a resistor as an electron barrier. It blocks the electron flow and reduces the number of electrons flowing through a conductor at a time. Consider these two circuits. Due to the resistor, the current has been reduced, and also the voltage across the light bulb has also reduced. Resistors can be categorized by their functional type. Fixed resistors have a set resistance value. Variable resistors allow adjustment of the resistance value. Special resistors, thermistors, change resistance with temperature. Photoresistors, LDRs, change resistance with light levels. As the name suggests, resistors resist the flow of electrons. They are like traffic cops for electrons, slowing them down as they move through a circuit. Imagine you have a 12-volt power source, and you need to power a light bulb that is labeled for 5 volt and 1 watt. If you connect the light bulb directly to the power source, the high voltage will cause too much current to flow through the light bulb, overheating and fusing the filament. This will destroy the light bulb. How can we solve this situation without changing the power source or the light bulb? This is where the resistor comes in handy. You can use an appropriate resistor to reduce the current flowing through the light bulb. By adding a resistor in series with the light bulb, you can drop the excess voltage and protect the light bulb from damage. To select the appropriate resistor, you need to calculate the resistance needed to drop the voltage from 12 volt to 5 volt. Here's how you do it. First, calculate the voltage drop across the resistor. The voltage drop needed across the resistor is the difference between the power source voltage and the light bulb voltage, which is 7 volt. Then determine the current through the circuit. The current through the circuit can be determined using the power equation we learned earlier. The power rating of the bulb is rated at 5 volt and 1 watt, so the current can be calculated as 0.2 amperes. Finally, calculate the required resistance. Using Ohm's law, you can calculate the resistance needed to drop 7 volt at 0.2 amperes. So you would need a 35 ohm resistor in series with the light bulb to safely reduce the voltage to 5 volt. Now let's talk about schematic diagrams. Consider this simple circuit. This pictorial circuit diagram uses simple images of components. But it is hard to draw these pictures clearly every time we need to sketch a circuit. When learning electronics, we draw circuits using circuit symbols. This is called a schematic diagram, and it shows the components and interconnections of the circuit using standardized symbolic representations. So this circuit can be shown like this. Using schematic diagrams makes it easier to draw, understand, and analyze circuits, ensuring clarity and consistency. Now it's time to dive into more advanced topics. In learning electronics, it's essential to understand how to analyze and interpret circuits as a whole. The main idea is that when you build a circuit, you need to ensure that the components can handle the voltages and currents they will be subjected to. These calculations are usually made after simplifying the circuit. Here we have the simplest form of a circuit with only a resistor and a battery. For this kind of simple circuit, we can directly apply Ohm's law and calculate the current. But practically, most circuits are not as simple as this. we need to learn how to analyze complex circuits like this. The key skill is calculating the total resistance of a resistor network. Total resistance is the overall opposition to the flow of electric current through the circuit. By finding the total resistance, we can simplify a complex network of resistors into a single equivalent resistor and reduce the circuit to this basic form, making it easier to design and analyze. Let's learn to analyze complex resistor networks step by step. There are two most basic resistor arrangements: series resistors and parallel resistors. Solving the series and parallel resistor is the first step of solving complex resistor networks. Series resistors are connected end-to-end in a single path. The total resistance of a series-connected resistor network is the sum of the individual resistances. Parallel resistors are connected across the same 2 points, creating multiple paths for the current. The total resistance of a parallel connected resistor network is found using the reciprocal of the sum of the reciprocals of the individual resistances. Let's solve a few circuits to help you gain a good understanding of how to use these concepts. Calculate the total resistance of this circuit and find the current drawn from the battery. We can see there are 3 resistors connected in series: 10 ohms, 20 ohms, and 30 ohms. So the total resistance is the sum of each resistor's resistance, which is 60 ohms. By calculating the total resistance, we can replace the 3 resistors by one resistor with 60 ohms resistance. Now we can easily use the Ohm's law to calculate the current. Let's move on to another circuit. Calculate the total resistance of this circuit and calculate the current drawn from the battery. We can see there are 3 resistors connected in parallel: 10 ohms, 20 ohms, and 30 ohms. So the reciprocal of total resistance is the sum of reciprocal of each resistor's resistance. It is a bit harder than earlier. We get the total resistance of 5.45 ohms. By finding total resistance, we can replace the 3 resistors by one resistor with 5.45 ohms resistance. Since we know the total resistance and the voltage, we can easily use the Ohm's law to calculate the current. Now we have a bit of practice solving series and parallel resistor networks. Let's try to solve a more complex resistor network. Can you calculate the total resistance of this circuit by solving series and parallel resistors? Let's start from these series resistors. The total resistance for these 2 series resistors is 220 ohms. We can replace these 2 resistors with a single resistor of 220 ohms. Next, I'm going to solve these 2 resistors which are connected in series. The total resistance for these 2 series resistors is 20 ohms. We can replace these 2 resistors with a single resistor of 20 ohms. Now there are no series resistors, but here we can see these 2 resistors are connected in parallel. So let's solve those. The total resistance is 18.33 ohms. Let's replace these parallel resistors with a single resistor. Now again we have 3 resistors that are connected in series. The total resistance is the sum of each resistance, which is 40.33 ohms. We can replace these 3 resistors with a single resistor of 40.33 ohms. Done! We have simplified the complex resistor network step by step using series and parallel resistors. This complex network is equal to a single 40.33 ohms resistor. Calculating the current is easy now. Just use the Ohm's law. The total current is 0.297 amperes. Now let's move on to our final topic of this video: voltage dividers. Take a circuit like this. We know the total resistance of these series connected resistors are the sum of each resistance. Now we know the total resistance and the voltage across those resistance. Using the Ohm's law, we can calculate the current going through the circuit. Now pay attention to the voltage across each resistor. Since we know the current on through resistors, we can calculate the voltage across each resistor individually. Do you notice that these resistors have divided the supply voltage? These kinds of circuit segments are known as voltage dividers. To put it very simply, a voltage divider is a circuit that, given a certain voltage input, produces a predictable fraction of the input voltage as the output voltage. The simplest voltage divider is shown in figure. With that, our first lesson comes to an end. I hope you enjoyed it.
If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.